a stereotype is a fixed general image or set of characteristics that a lot of people think and believe reflects on some particular person or a thing, which means they are not completely true or not always true. So keep it in mind. And if you haven't spotted it yet, I'm here for you. There are some matching points between the stereotypes about artists and scientists. So they both can be crazy about their ideas. For example, Nikola Tesla slept only 2 hours a day, believing that sleep was a waste of time. I think you all have been there at some point. And he also conducted experiments on electricity on himself. And there is, for example, Marina Abramovic, who in her performance, The Artist is the Present, sit still for 9.5 hours a day for 3 months, making eye contact with strangers. No pee breaks, for real. Yeah, so you see. So sometimes, yeah, exactly. And they also need the creativity. It is a must. You know, that feeling that you just step into your shower and then this thought strikes you, like, I have to write it down right now, or those ideas that keep you up at night. And also they both need discipline and consistency in mastering their skills, and sometimes they are way ahead of time with their ideas. For example, Hieronymus Bosch, in 15th century, painters usually painted some religious motifs in realistic manner, but he created some nightmarish landscapes with hybrid creatures, with monsters, and some surreal symbolism. So he was about 400 years ahead of time when Salvador Dali picked up on surrealism. Or, for example, Gregor Mendel. In 1860s, he discovered the laws of genetics by studying pea plants. And his works were rediscovered 16 years after his death, proving that he actually unlocked the laws of DNA before DNA was ever discovered. So, artists and scientists, they are sometimes also controversial characters, as well as our first presenter. So he is an old guy and a young kid in a body of a 40-year-old guy. And he is an old guy because he drives like a grandpa, he forgets things, and what else do you do? Yeah, forgets things, as well as me, we all do. And also he is a young kid because he is very easy to impress, and he likes building and playing with Lego. And Thomas here. As well as artists, they are many things. They are sculptors, they are painters, they do framing by themselves. And Thomas is Mädchen für alles, or one-man show in the area of wafer bonding, and he will tell you now why. So, big applause to him.
Once in a land far, not this land, far, far away, there was a king whose name was Gordon, King Gordon. His followers used to call him Gordon Moore, CEO of Intel, but to be honest, nobody really knew why. King Gordon lived in a land of many kings, and every 2 years there was a tournament to find out who is the king of the kings. And usually, King Gordon was the winner. The secret of his success were his wizards. They worked in their wizard workshops, which they used to call clean room. And there they created mighty and powerful warriors, the silicon wafers. And what made these silicon wafers so mighty and powerful were the transistors that they built on them. Because with their help, they were able to create mighty and powerful weapons. One of the most feared of this time, I'm pretty sure you all know, it was called the brick. So, the goal was to win this tournament. That's why the wizards had to improve their wafers, which means they had to improve their transistors. And Now, it wasn't like King Gordon didn't trust his wizards, but he had sure to keep on winning this tournament because he loved being the king of the kings. And so he decided to finally clinch his power and his success to enact a law. This was called Moore's Law. It said that the amount of transistors in an integrated circuit has to double every 2 years. And so his wizards did as they were commanded. They got back to work, they followed the law and made the transistors smaller and smaller and smaller. And so, of course, also their weapons became more and more powerful. And it looked as if this development could go on forever. But after several years, some of the wizards realized that they were running into some serious problems. The first problem was, like it always is, the money. Because with every scaling, they needed new processes, new tools, new materials, and they are all very expensive. The next problem was that the smaller they made the transistors, the more and more complex and difficult their production became. And in the end, at some point, even physics said, stop, you can't get any further. So with that in mind, the wizards went to the king and to talk with him about their concerns. But yeah, King Gordon, he was very old and very hard-headed, and so he only said, "The law is the law. Now go and make them smaller." And so the wizards did as they were commanded. They got back to work. But they knew that they couldn't go on like this forever. So that the king wasn't willing to change anything, but they had to change something. So they decided to talk with the king's evil twin. He never liked Moore's law. He always said, there has to be more than Moore. And yeah, by the way, he always had an eye on the king's throne. So up to these days, the wizards always have been very, very loyal to the king. But this had changed. And so King Gordon's evil twin took his chance. He built a new clean room for the wizards and promised them everything they needed. And so the wizards of More Than Moore were born. But as the king said, the law is the law, and we don't break the law. But to achieve your goals from time to time, you have to, maybe bend it a little bit. And so the wizards started their research. As one day, chance played into their cards, because during an experiment, one of the wizards dropped a wafer, and the wafer fell face down on the floor. And as the wizard saw that, he had a brilliant idea. So he called his colleagues and said, "Guys, come over here, come here, look at it, look at the wafer back." And the others were like, "Yeah, well, there's nothing." Exactly, there is absolutely nothing. So if we aren't able to make the transistors any smaller, why don't we use the back and put something there? The wizards liked that idea, but if you want the back to work with the front, you somehow need to connect both sides. So they thought about how they could do it. The first idea was, okay, what about using wires? To be honest, this option didn't look very promising. So they thought about it again. What about if we put the connections through the wafer? So there is something that we call TSVs, through silicon wires. To create these TSVs, you take a silicon wafers, add holes in it, and fill them with metal. This works quite good, but the aspect ratio is a problem. That means the smaller you make the TSVs, the less deep you can make them. So now that the transistors already were very, very small, also the TSVs had to be very, very small. So small that they could only be created up to a depth of about 70 micrometers. But the thickness of our silicon wafers usually is 720 micrometers. So they needed to find a solution how to contact the TSVs from the back. So what about making the wafers thinner? Yeah, you can do it with a grinder, it works pretty good, but the problem there is, the thinner you make the wafer, the more and more the stability decreases. And I think you can imagine that it's hard to handle a wafer that looks like this. So okay, up to now you only heard there are problems here and problems there, and this doesn't work and that doesn't work, but I would not be here talking about it if there wouldn't be a solution. And the solution is called temporary bonding. And that exactly is my daily work as a wizard of More Than Moore, or as you might call it, as a process engineer. The idea of the temporary bonding was as simple as brilliant. So if we aren't able to handle this wafer when it is so thin, why don't we take a second wafer, put it in front of it to make it more stable? And that's what we are doing. In our case, with the help of adhesive and a so-called dual layer bond. And this is how it works. First, you take your device wafer with the transistors and the TSVs. This is put into the spin coater where adhesive is applied. Then the wafer is rotated so that the adhesive can spread all over the wafer. Then the wafer is put on a hot plate for a short thermal treatment to get rid of the solvents and to pre-cure the adhesive. The same then is done to the carrier wafer. In our case, we are using blanket silicon wafers and another type of adhesive. The process flow is the same, so coating, spinning, and hot plate. Now you can take both wafers and put it into the bonder. First the device wafer, and then the carrier wafer. Both wafers are bonded by applying just a small amount of pressure. After that, the wafer stack is again put on a hot plate to get its final thermal curing. And this is how the dual layer bond works. So, as already said, we have two wafers with two different kinds of adhesives. During this final thermal treatment, an intermediate layer is created in between these both wafers. This intermediate layer provides a very strong bond to keep both wafers together for the following processes in the clean room, but at the same time it enables us to pretty easy debond the wafer when we want it, by just applying the right force at the right place. Okay, so now that the device wafer is bonded to the carrier wafer and is stabilized by the carrier wafer, we can flip the whole stack around and thin down the device wafer backside. This is done in our grinder. Usually the desired thickness is about 60 micrometers, so that the TSVs are already opened. And then the magic happens on the backside. But for that, we have to give the wafers to our wizard colleagues in the other clean room. What they do there depends on what you want to achieve. So you can put a full metal layer on the back to use it as a grounding. You can connect the TSVs with one another, or you can put pads on the back to bond something else there. So there are a lot of options, but I don't want to go in detail at this point because that's too much stuff. That's so much stuff to fill enough. Lots and lots of other stories. Maybe someone of you might tell in the future. So, when our wizard colleagues in the other clean room are done with doing magical things on the backside, the wafers come back to us. And what we have to do there is separate both wafers. So, not exactly like this, but we do need a blade. This blade is shortly inserted in between both wafers and directly pulled out again. With that, the intermediate layer is cracked and the debonding process is initiated. After that, we have to apply a tape and a frame on the device wafer backside to give it more stability again, and then the carrier wafer can be debonded by gripping it and tearing both wafers apart. What we have to do then is a cleaning step to remove the remaining adhesive from the device wafer front, and that's our final result. But enough of talking about what I do. I'm really sure you want to know how the story of King Gordon and his evil twin ended. The wizards of Northern Moor, they spent a lot of time and they did a lot of research. And as they finally felt ready, they challenged the king. They fought one tournament after the other. Some were won by the king and some by his evil twin. But all of them were pretty close. The last tournament took several weeks and it ended drawn. At this point, the king and his evil twin realized that they were not able to defeat the other. They were dependent on another, because with every small development, with every little step forward, also the other got a little bit better. And so they started talking, and they came to the point where they said, okay, it's stupid to fight each other. But what about fighting together? And so they decided to merge. And within a short time, they became the biggest kings of all time. They first took over the land, and then the whole world. And what about the wafers and their weapons? Of course, with every development, they became stronger and stronger and stronger. Thank you very much.
Beautiful presentation. It gets better each time. Okay. So, coming back to the stereotypes about artists and scientists. Some stereotype, they touch on money, like scientists and artists, they work so hard but died so poor, and also on the sense of community, like belonging to some eligible group, meaning saying, I'm an artist, I'm a scientist, feels kind of cool, So I was curious, who is actually more numerous and who earns more money in the end, scientists or artists? And before we look into statistics, buckle up because there will be some quizzes. Remember last time there was a quiz and nothing changes. You get your chocolate if your guess is right. Okay, so the first question is who is more numerous? This is just a warm-up, not a chocolate question yet. I'm giving you the information right away. So scientists and engineers make up 50 to 60 million people globally, whereas artists are more numerous. They make up 100 to 150 million people on Earth. But the question is, who makes more money? You know it, right? Scientists and engineers make more money even though they are fewer. But 1% of artists, like the wealthiest artists, earn exponentially more than the wealthiest scientists. Fun fact. And I was thinking, was it always like that? The thing is, no, it wasn't. And the landscape of artists and scientists changed tremendously throughout the centuries. And I will show you how. So in the Renaissance, top artists like Leonardo da Vinci, Michelangelo, Raphael, they were very, very respected, very wealthy because they were supported by the church and the royalty. Scientists as a profession was not there yet. So scientists of that time, they were polymaths, alchemists, or in the best case, philosophers. And they were often poor and even persecuted for their ideas. For example, Copernicus, his work was so complex that it was not understood at first. So he avoided immediate backlash, but only because they didn't even get it. And Galileo Galilei, for example, his contemporaries thought that he was very arrogant by questioning the wisdom of centuries. And many of them genuinely thought that he had lost his mind by claiming that Earth was moving when they couldn't feel it. The Enlightenment, as the word says, was better for scientists. The first academies of science emerged, and it was better. And for artists, it was still very well. The situation looked good. In the Industrial Revolution, science emerged. And it was the time of wealthy inventors, as for example, Ford and Edison. Thomas Edison alone had more than 1,000 patents. The artists were still doing good. And the 20th century. Here, the gap between the rich artists and not very rich artists was rising. It was the era of first billionaires. First billionaires artists like Walt Disney, Andy Warhol, or the Beatles. It was also the golden time for the scientists because there was high demand for medicine, physics, technologies. And the tendency remains. So there was one big plot twist somewhere in the middle, and you guys, you scientists, you are doing better. So the quiz is coming now. So there is this top 1% of the wealthiest scientists and artists. You have to tell me now, who is the wealthiest artist and who is the wealthiest scientist of all times? First, the wealthiest artist. And before you say, how are we supposed to know? You know it, I'm sure. And so the artist is the fine artist person, and the scientist is a scientist or inventor, not an entrepreneur. Okay, here we go. The artist. Oh. Fine arts. Fine arts. This I heard, yeah. Okay, you want it? No? No? No, it's fine art. A person who is painting, basically. True. Who said what? Very close. Yes, yes, it is Picasso. Okay, so where is my chocolate? So the first chocolate, as promised, goes to the first. Okay. Now the wealthiest scientist. Not entrepreneur. Pure scientist guy, okay? You know him, come on. Who? No. You will be surprised, you just heard about him. No? Yes, who said that? You. Okay, so we have Picasso and Moore as the wealthiest. Okay, so as we are all sitting here and you're all scientists, engineers, I see that you prefer stable income and being respected. But sometimes you can be also risky with your research, depending on the grade of your research and the nature of your research. But in general, you have to keep in mind two things to make your research a success. Follow strictly the rules, well-defined rules, and experiment a lot. So our next presenter's way of learning new sports is doing everything, even if it doesn't include following the rules. So she was learning how to play squash by catching the ball instead of hitting it with the racket. So it's like a research. You try out different methods, you see what works best. Also, she is fluent in 5 languages, but unfortunately, when it comes to German. But I think it's not entirely true because she has been exposed to German a lot. And she will tell you why. Give applause to Keerthi.
Hi, everyone. So last year, I made a very important decision, which is to get a driving license. So I did my theory classes, I took the exam, everything was pretty easy. So I felt, okay, how different will it be from the practical part? So this image gives you the difference I felt between theory and practical. So the first day after my driving class, I came home with this expression. I was just thankful for not having an accident. So when I was sharing this frustration with my Gen Z nephew, he gave me 2 solutions. First one was give up, you don't have to try. And the second one is you can just buy a smart driving car. You don't have to do anything, right? So he's right in both the cases. So let's just look into the smart driving car. How does it work? It has numerous sensors, takes the input of all what it sees on the street, stores this data, computes it to give the corresponding output, right? It works perfectly here in Germany where the rules are clearly defined. Now, what happens when you drive it in my home country? Yeah? I'm sure most of you didn't notice this red light because no one in the street cares about it, right? And where is the street actually? But the sensors should also have the culture of the country because you can own a Lamborghini in India, but give importance to the buffalo, okay? So what happens here? You have too many inputs, too many outputs, right? So what happens? This numerous data is being transferred between the computing part and the memory part. Problem, energy consumption if there's too much of data. What do you do when you have a problem? Use your brain, right? To solve any kind of problem. Here, literally look into your brain. So the brain has numerous neurons, and the synapses has a parallel way of communicating the information, which makes it 10 times more efficient than your computer. So let's just get inspired and have the similar kind of architecture. Yeah? And to get this architecture as efficient as the brain, we can use the memory element here. It's resistive random access memory. How does it work? It cycles between two different resistance state, low resistance state, and a high resistance state. For analogy's sakes, let's just keep in mind it's like the engine revolutions of your car, low and high. And here, the insulator plays a more important role. As you can see, it's very thin, few nanometers thick. How difficult can it be to fabricate it? Well, this is how it feels. Just like in driving, where I felt that it was a multitasking job to concentrate on the street signs, be on the lane, and also look after every other thing on the street. It's the same thing while fabricating. It just has to follow many requirements of the fabrication. It has to be a CMOS-compatible layer, operate at a low operation voltage, needs to be scalable, and if you're fabricating many devices, lower variation as possible, right? So now I have the insulator layer. How do I fabricate? Just like in driving, you can have many destinations, right? But you have to choose the one right destination. Exactly, in fabrication, you have many different ways of fabricating this layer, but you have to use the one right one. For this application, it's atomic layer deposition. So now you know the destination. What do you do in the Autobahn? Merge, right? So there are different spots to merge, but there is always one right spot. Any other spot will cause accidents. It's the same thing for fabrication. There is just one optimal process window. Anything lower or higher, you have higher temperatures, impurities, which will affect your device performance. But just before merging, there are 3 important German rituals you have to do, which is Spiegel, Blinken, and Schulterblick. Exactly with fabrication, just because I know how to fabricate, I cannot go to the clean room with this smiling face. There are 3 important rituals which are done in technology department, which is Step Manager, Factory Works, and Lot Browser. Yeah? So now I know all the rituals, but there are still some more important German roots, which is Rechts for links. Yeah? So just because I can fabricate this device, I cannot just use it in the technology. The priority here is that this device does not affect the performance of other devices in the technology. So that's the priority here. Now, I know how to drive. Now I know how to follow all the rules. I can just keep driving, right? But still, there is one thing which can stop me. That's the red light. So there's an exact replica of these lights for every tool in the clean room. So just when you have everything ready to fabricate, this red light can stop you. Unlike the streets, in the clean room, it's days, weeks, and sometimes months. And the final task of driving, which is the parking. I see experts finding a spot, and then their car is just there in the parking spot. For me, it looks like this. It feels like I'm solving mathematical equations for the right angle, speed, distance, and also not to hit something which I didn't see. It's the same thing in clean room. The final step is to create a recipe in the tool. So it's not just about finding the optimal process window. You have numerous other settings which has to be set at the right point for the fabrication. Yeah? And finally comes the test. For both driving and for the devices I fabricate. It's the same rules for both. Either I pass, I'm happy, or I fail, learn from the mistakes, improvise, and repeat all the steps again. So coming back to my Gen Z nephew's question, why am I still learning when I can easily give up? Well, I'm working in a clean room. It's basically like driving a car. I showed you all the similarities. And what about RAM devices? Maybe I can drive this car in India sometime in the future. That's all.
Thank you. Another beautiful presentation. What's happening here? Okay, coming back. Artist, scientist stuff. Okay, so if you're on social media, then you must know this kind of trend, which is the flash mob called the artist and the art. And on social media, it's something more or less laughable like this, but we are keeping it in a serious fashion. And here is a British Indian sculptor, who is known for his massive mirror-like structures and artworks. This is Anish Kapoor, and it is his artwork, which is called the Cloud Gate or the Bean in Chicago. So everything is super clear. This is the artist, this is his art. Oh, sorry. Okay, so, but it can't be that easy all the way. So I will now give you a fragment, a tiny, tiny piece of an artwork, and you will try to guess where does it come from. Any ideas? No more chocolates here, but you can still try. No. Okay. And it's a tricky one. This is the beard of Van Gogh from his self-portrait. Let's try another one. This teeny tiny part of a massive, big, very well-known artwork, which is... This is very, very close. Very, very close. Yeah. Wow, that is worth a chocolate. Let me get back to you. Okay, so this is The Birth of Venus by Sandro Botticelli. And I will give you something which is maybe closer to your heart. This fragment, or this, any guesses? Okay, you know what it is. Ladies and gentlemen, this is a chip. A chip which is a pure art. Pure art. You know what else is considered art? Is the food. The food, yeah, it was like this before. It will be like that in the future. Artists will always get inspiration from food. But it can also be twisted another way around. Paintings can be recreated in food. It's a never-ending circle. And our last presenter, who is a circuit designer, he not only likes putting things into artistic order on his chips, he also likes doing that on his plate. He loves cooking. And not only he likes every structure be perfect, he also likes his life and work being very well structured. He loves everything scheduled. He schedules meetings to schedule meetings. And we scheduled this day 1 year ago, so I'm very happy you showed up. So, give applause to Max.
Okay, I have to see that I activate this headset. Okay, you can hear me, because there's some special things involved in my presentation, so I need my hands free. So, hello everyone. Let me see this side. Okay, so you might know the situation. You're with your family or friends and you sit together for dinner and they ask, yeah, so you're working at IHP, but what are you actually doing there? What is your job? And then what I usually say is like more or less the official job description that I have in my LinkedIn profile. I say, I'm a mixed signal IC designer for neuromorphic computing. And then they look at me. And so I say, okay, come on, I'm designing chips for AI. And usually what I see then is something like this. So some people are falling asleep and others look confused. And so what I'm thinking, what goes through their head is something like this, yeah. And then I have to come up with a more creative explanation, yeah. And so what I say is making chips for AI is nothing else. No, I have to change a bit my outfit for that explanation. It's nothing else, you can already guess it. Like cooking, yeah? Yeah, you laugh, but I will explain you why it is like this. So first, in cooking, you need inspiration, you need to be hungry. So you need ideas. So what you do is usually you look through a recipe book and you browse through the recipes and you say, okay, this one might be interesting to cook. Similar in circuit design. I sit in my office going through books, and then at some point I look through the circuit ideas and I find one and I say, hey, yes, that's a great idea. I will pitch that idea to a colleague. So I go to a colleague's office and say, look, this is a circuit idea, this recipe I want to try out. And then we have a discussion, and there's some confusion involved, and he explains me why I can't do this in reality. And then we discuss scientific discussions, and in the end, we come up with a solution which both fits us, and then we call this in circuit design the application level, the system design. Yeah? So what comes after the system design is same like in cooking, the dish has only as good as the ingredients and tools used for this dish to cook it, yeah? And same in circuit design, so we have different kinds of ingredients we can choose from, like resistors, capacitors, transistors, and same like in a cooking dish, there has to be a special ingredient, yeah? So this is, by the way, how I imagine myself when I cook and then put the special ingredient. And my family looks more at me like this. So in case of circuit design, we heard that ingredient before. It's resistive random access memory is our special ingredient. It's a very small device with a size of only 600 times 600 nanometers, 5 nanometers thick. So I asked ChatGPT, what is it comparable in terms of a cooking ingredient? It said, it's smaller than any cooking ingredient. Maybe this protein, which is in cheese, which is casein. So I don't know in the end if our chips smell or taste like cheese, but maybe some of you have tried, I don't know, okay. So, but also with these ARM devices is where the AI comes into the soup. Because our ARM device as an adjustable resistor is nothing else than an electronic synapses, and we can build small brains with this electronic synapse. So we use new devices and materials for circuit design, but now to the actual cooking part. This is where my part comes in. So first I have to draw and simulate the schematic with all these ingredients, with all the transistors, capacitors, resistor, ARM devices. And it's like testing new dishes. So I test out at my office new dishes. And then I have to draw that layout from the schematic to the layout. And you find the same ingredients here again, the capacitor, the transistor, the ARM device. So it's about making everything look nice, same to cooking. Yeah? So in the end, it has to look nice. But what it actually looks like, this process, so I romanticized this a bit, but actually it looks like this. I'm sitting at the desk, looking there, pulling my hair, going crazy, and it feels like this, yeah, the circuit design part. So I'm going crazy there sometimes. So this is the circuit design part in the middle. And the cooking part is then also partially done by our clean room, who assemble our chips. And this would be the fabrication step. But now every food has to be taste tested, and so are AI chips. And what is taste testing in terms of AI chips? It's I go to the lab and I measure the chips. So I look at them, and then they might not work, so I go crazy again. So you see already some measurement equipment flying around. So I measure them 1 month, 2 months to make that AI chip really work, sometimes 1 year. And in the end, they always work, and then I'm happy. Yeah. And so this is the testing part, which comes in the end. So I showed you the whole process of the circuit design flow, but really we are only as good as we compare to competitors. So we have to compare to competitors to evaluate if our chips are really good. And one AI chip competitor is NVIDIA, so they make chips in large quantities, very cheap, big chips, and when you compare this to food, it would be something like this, like your favorite fast food joint. It's quick, it's cheap, it gets the job done, it can be produced in large quantities, and also you look at the CEO, he sells it good, he has that cool leather jacket, but we can also wear a leather jacket and hold up a nice board in the end. And when you would compare it to a dish, it's more application-oriented, specific, more nice, which you might enjoy a little bit more in the end. Yeah, so that's our competitors, and like I shown you before, the whole process where I am in the middle, sometimes going crazy, sometimes being happy, but all these things, same like cooking, wouldn't be able to do without the other cooks, the colleagues, and so this would be the Aram team cooking with me here at IHP and me in the middle going crazy. Thank you.
Thank you. Yes, right. Okay. So after all this impressive presentation, there must be like something, it's here. Okay. there has to be something inspirational. And so there must be some inspirational conclusion. So actually, artists and scientists, they actually are quite alike. The appearance may be different, but the approach is similar. And it actually is cool calling yourself a scientist or an artist. And actually, after this last presentation, I want to say scientists are artists. So please stop? No, not stop. Don't stop embracing it. Yeah, and if you want to create impressive presentations like this, please feel free to contact us and join our group. Thank you for coming.